Hey guys, today we're going to learn about related rates. Now, what a related rate is a problem where you're trying to find the rate at which something is changing by relating it to other known quantities that we know about that problem. Now, a rate of change, because these are now going to be real-world applications, when we find their derivative, a rate of change is always with respect to time. So when we were doing implicit derivatives, we always found the derivative of y with respect to x. But now, all of our variables, we're not going to really have x or y. We're going to find the derivative, and the derivative of any variable is going to be with respect to time. So let's look at some of these most commonly used equations for related rate problems and how to take the derivative and what it represents. For the first one, it's the surface area of a sphere, which is the equation A equals 4 pi r squared. When we take the derivative of this equation, we have two variables. We have A and r. So when we take the derivative of A, that is going to be dA dt. Just like how we do dy dx when we're taking the derivative of y with respect to x. Is going to equal to, now r here is my only variable, so I'm going to apply the power rule here by taking the 2 and multiplying it to the 4 pi. So that would be 8 pi r, and now the derivative of r, remember just like we do with implicit when we take the derivative of y and then you multiply by dy dx, we do the same thing. The derivative of r would be dr dt. Now what this represents, dA dt, is the rate at which area is changing. Dr dt is the rate at which the radius is changing, because that's what r represents. Moving on to the volume of a sphere. The equation for volume of a sphere is V equals 4 over 3 pi r cubed. So we do the same thing as we did before. The derivative of V would be dV dt is going to equal, now I'm going to multiply the 3 with the 4 over 3, so that would be 4 pi r squared, and then the derivative of r, which is dr dt. Now dV dt is going to represent the rate at which volume is changing. And dr dt is the same as this one here, the rate at which the radius is changing. Now here we have the equation A equals the square root of c squared minus b squared. This equation comes from the Pythagorean theorem. So now it tells me here that c is a constant. If c is a constant, then when we find the derivative of the inside, we don't have to do the dc dt because c is not changing, so it does not have a rate of change. It would be another number, just like, let's say, pi or 4 or whatever. So the derivative of a would be dA dt is going to equal to, now remember that this is a square root, so this is c squared minus b squared raised to the 1/2. So I have to apply the chain rule here. I'm going to take the 1/2 and move it to the front, so that'll be 1/2 c squared minus b squared raised to the negative 1/2 times the derivative of the inside, which the derivative of a constant would be 0, and then the derivative of negative b squared would be negative 2b dB dt. Now, of course, with any of these derivatives, we never want to keep negative exponents because we are going to be plugging in numbers. So I would rewrite this using only positive exponents. So dA dt is going to equal to, now the only thing that's going to stay in the numerator is this negative 2b, as well as the 1 here. So 1 times negative 2b dB dt would be negative 2b dB dt, and this is going to be over. This is all going down to the denominator, so that would make it a positive exponent. And the exponent of 1/2 is a square root. So that'll be the square root of c squared minus b squared. Now dA dt, when it comes to the Pythagorean theorem, this is talking about some triangle. So if this is A, B, and C, the dA dt is going to be the rate at which side A is changing. And dB dt is the rate that side B is changing. Let's look at some other commonly used equations for related rates. The next one is the volume of a cylinder. And we have V equals pi r squared times h. Now here I'm telling you that r is a constant. And so that means that r squared is another number. So when we take the derivative of this section here, we don't have to apply the product rule because r squared represents a number that does not change. So my derivative here would be dv dt is equal to, remember this all represents a number, so pi r squared and the derivative of h, which is dh dt. Where dh dt, h represents height, so that would be the rate at which the height is changing. Next, we have a trigonometric function. And we will be using all trigonometric functions, or rather the three basic ones, sine, cosine, and tangent. I just chose to do cosine because the derivative would be the same, or the same process anyway, for sine and tangent. So when we take the derivative of cosine theta, we know that that is negative sine theta. But then we always have to multiply that by the derivative of the angle. My angle is a variable, which is theta, so that derivative would be d theta dt equals, now x over 15 is the same thing as saying 1 over 15x. So the derivative of this would be 1 over 15 and the derivative of x, which is dx dt. dx dt is going to be the rate at which this side is changing, much like the a dt and db dt from the previous slide. So d theta dt is going to be the rate at which the angle theta is changing. This last equation is the volume of a cone, which the volume of a cone is V equals 1 over 3 pi r squared h. Now in a cone, the radius and the height are always different because this is what a cone looks like. So depending on where you are along the cone, the radius does get smaller the more you go down, and the height would also change depending on where you are along the cone. So the derivative of the volume of a cone, we would have to use the product rule for this r squared and h. So dv dt is going to equal to, I'm going to use this as my first part and this as the second. So the derivative of this would be 2 over 3 pi r dr dt times h plus, now I'm going to leave that first part alone, 1 over 3 pi r squared and the derivative of h, which is dh dt. Now when it comes to cones, we're going to be using a different method so that we don't have to go through this product rule, but just so you understand how to find that derivative. And I put here that you got to keep in mind that there may be different variations to the derivatives depending on what kinds of information is given in the problem. We may have constants that we can plug in, so our derivatives could change. But in general, these are the most commonly used equations. So now let's look at what a related rate problem would look like. Okay, so with this particular problem, We have air is leaking out of an inflated balloon at a rate of 230 pi cubic centimeters per minute. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? So we gotta dissect this. Now, usually the problem with related rates is that there are too many variables, and we need to figure out what they represent and how we can relate what we're looking for to some equation that ties in all of these variables together. So I have here basically like some steps that you can follow to help you with these kinds of problems. Keep in mind that this is more of a general guideline, and related rate problems are usually very different from each other. So the first step that I have is draw a picture or diagram if you feel like that's necessary. I'm a visual learner, so I normally like to draw a picture. For this one, it's not really necessary, but let's just draw it out anyway. Here we have a balloon. Okay. Air is leaking out at first of all, notice the word rate. And we have 230 cubic centimeters per minute, 230 pi, excuse me. Whenever you see this word, cubic, that implies volume. The only time that your units of measurement are cubed is for volume. And if your units of measurement are squared, that's area. So since this is a rate, and this 230 pi represents volume, that means that I am given dV dt. Additionally, air is leaking out of the inflated balloon. So think about what would happen to this balloon if air is coming out of it. That means that then the balloon would get smaller. And if it gets smaller, that means that the volume is decreasing. So this rate would be a negative 230 pi. I mean, remember what we've done with derivatives. If the derivative is negative, that means that the function is decreasing. If the derivative is positive, that means that the function is increasing. Since this represents the derivative of volume, and the volume is going to decrease, that derivative will be negative. So dV dt is equal to negative 230 pi cubic centimeters per minute. And I usually like to write out everything that I'm given in the problem, including the units. So that way it kind of shows me all the variables that are involved. The next thing is that at the instant when the radius is 4 centimeters, so that's my radius, 4 centimeters. What is the rate of change of the radius of the balloon? So that means that I am looking for dr dt, since dr dt represents the rate at which the radius is changing. So I've done one by drawing a picture. The next step is to find an equation that relates all of the information given and look to geometry for many formulas. Now, we have done a lot of the formulas right before, and just in case, I also gave you in class the reference sheet of all of those formulas. Since this is dV dt, that must mean that I'm going to have to use the volume, and the shape of a balloon is a sphere. So I'm going to use the volume of a sphere, which is 4 over 3 pi r cubed. So I have identified the equation that relates all of this. The next step is to substitute in the formula any constants that you may have. Now, a constant would be something like, let's say, the radius. But since the balloon here is deflating, the radius is going to change. So this is not a constant. So I can't plug anything in. So we're going to skip this step. Step 4 is to differentiate implicitly with respect to time and use all differentiation rules that apply. So I am going to differentiate this like we did earlier. So this would be dV dt equals, multiply the 3, so 4 pi r squared dr dt. Step 4 is done. Step 5, plug in provided information to solve for the desired quantity. So we're going to look at what I have here. I have dV dt, so I'm going to plug in this as negative 230 pi. is going to equal to 4 pi, and we're given the radius at that moment, which is 4 squared. And then I'm looking for dr dt. And now I can use this to solve. Notice that I have no other variables now. The only variable I have is the dr dt, which is exactly what I'm looking for. So negative 230 pi is going to equal to 4 pi times 4 squared, which is, this here is 16, and 16 times 4 pi is 64 pi dr dt. To solve for dr dt, I'm going to divide the 64 pi. Here, my pi's would cancel, and so dr dt is going to be negative 230 over 64, which you can leave like this as a fraction, or if you want, you can go to the calculator and we can divide. Negative 230 by 64 is going to equal to negative 3.5937. And then we're going to write out our units. The only time you have to worry about your units having any kind of exponent is for volume or area. Since this is the rate of change of the radius, then it would be centimeters, and then over the unit of time, which is per minute. So that is your first related rate problem. We're just going to practice lots of different types now. Let's look at another one. Water is leaking out of a cylindrical tank at a rate of 3 cubic feet per second. If the radius of the tank is 4 feet, at what rate is the height of the water changing? So let's draw a picture. Here is my cylinder. Water is leaking out of the tank at a rate of 3 cubic feet per second. So again, here's that word cubic. That's volume. If water is leaking out of the tank, that means that the rate at which the volume is changing is going to be negative. So dV dt is going to equal to negative 3 cubic feet per second. So all rates are always your unit of measurement over the unit of time. Just so if you ever get confused when you're writing your units at the end, that's why whenever I'm writing down everything at the beginning, I always include the units so I can always go back and look at it and make sure what units I'm using. If the radius of the tank is 4 feet, so my radius is 4, at what rate is the height of the water changing? I'm looking for dH dt. So I always start off the problem this way. I write down all of my given information as well as what I'm looking for. Now, because I was given dV dt of the cylinder, that means that I'm going to have to use the equation for volume of a cylinder. The volume of a cylinder is V equals pi r squared h. Now you see here how I have two variables. However, in a cylinder, no matter if my water is here, the radius of that part right there of the cylinder is 4. And if my water is here, it's still the same because the radius of a cylinder stays constant no matter where the water is in the cylinder. So I can plug in before I even differentiate my constants. So that's what I have here. Constants, values that never change over time, can be plugged in before you differentiate, much like the radius of a cylinder. Versus if we were given a cone, if water is up to here, my radius is different than if the water is here. I would not be able to plug in the radius until after I differentiate. So I'm going to go ahead and plug in my radius now. So this is going to be pi 4 squared h, which is equal to 16 pi h. This is my equation for the volume of this particular cylinder. Now I'm going to find dV dt, which this is a coefficient to h, so this is going to be 16 pi, and then the derivative of h is dh dt. I can now plug in my dV dt, which is equal to -3 equals 16 pi dH dt. To solve for dH dt, I am going to divide by 16 pi. So the rate of change of my height, dH dt, is -3 over 16 pi, and my units would be feet per second. Here, remember, there is no exponent to my unit of measurement because this is not area, nor is it volume. So my unit of measurement is always singular. So that's why it's feet, and then always over time, which is seconds. Now, when you're doing these problems, you can also look at what you got as your answer and make sure that it matches what the problem is saying. If the dH dt is negative, that means that the height of the water is going to decrease. And if water is leaking out of the tank, that's exactly what's going to happen. My water, let's say, starts here, and then it's going to go down to down here. So the water level is decreasing. Now, let's look at a cone problem. So we just did a cylinder, and now we're going to see the difference with a cone problem. As I read this question, I'm going to go ahead and start writing out all of my given information and drawing my diagram. A cone has a diameter of 10 inches and a height of 15 inches. So here's my cone. It's got the diameter. We don't use the diameter, we use the radius. And the radius is always half of the diameter. So my radius is 5 inches. The height of my cone is 15 inches. Water is being poured into the cone so that the height of the water level is changing at a rate of 1.2 inches per second. This right here, since this is the rate of change of the water level, the height of the water level, so this is dH dt. And since water is being poured in, that means that the height of the water is going to increase. So this is a positive rate, 1.2 inches per second. At the instant when the radius of the exposed surface area of the water is 2 inches, so when the radius is 2, at what rate is the volume of the water changing? So we're looking for dV dt. Now, how am I going to go about solving this problem? Let's look at the equation for the volume of a cone. It's V equals 1 over 3 pi r squared h. If I was going to differentiate this just as is, r and h are both, they're not constants. So we would have to use the product rule like we did earlier in the lesson. However, to avoid this, and this is what I have in blue, I put here, most cone problems will require you to write a ratio of the height to the radius so that you can rewrite the equation of the volume of the cone in terms of one variable rather than two. So what this means is that cones, the radius and the height are proportional, meaning if the radius is going to decrease, the height is also going to decrease at the same exact, well, not at the same rate, but in the same proportion, in the same ratio. So we're going to create a ratio of the radius to the height, which in this particular cone, the radius, when the radius is 5, the height is 15. So this is the ratio of the radius to the height, which can be simplified to 1/3. Now what I do with this ratio, so let me just rewrite this here simplified, r over h equals 1/3. I'm going to use this to solve for either r or h. You can, and it does matter which one you solve for. So it depends on the given information here. You look for which rate you're given. I'm given dH dt. So that means that I want my equation to have only h's. So that way, when I find the derivative, I only have to, when I find the derivative, I will have dH dt rather than dr dt because I don't know what dr dt is. So if I want my equation to have only h's, then I'm going to solve for the opposite. I am going to solve for the radius. In order to solve for the radius here, I am going to multiply h to both sides. So the radius is going to equal to 1/3 times the height. Now I am going to hold on to this, and what I do is I'm going to plug it in here into my volume equation. So volume is going to equal to 1/3 pi. My radius is 1/3 h and then squared times h. So all I did was I took this and I substituted the r here with what that equals to. Now we're going to rewrite this so it's a little cleaner. This is v equals 1/3 pi. When you square a fraction, you square both the numerator and the denominator. So this would be 1/9 h squared times h. Now let's multiply my fractions and multiply the h's. So v is going to equal to 1/27 pi h to the third. See, the reason why we did this is we took my volume equation here that has two variables, and now we wrote it with only one variable. At this point, we are now going to do what we've been doing with the other questions. We are going to now differentiate it. So dv dt is going to equal to, I apply my power rule here, so 3 times 1/27 would be 3/27, which can be simplified to 1/9 pi h squared times dH dt. At this point, I'm going to start plugging in everything that I got. dv dt is what I'm looking for, so I'm going to keep that. Is going to equal to 1/9 pi. And now here I'm missing h. I don't know what h is. But here's the good thing. Even though I don't know what h is, I do have this ratio and I was given the radius. So if my radius is 2, I can take this and plug it in here and use it to solve for h. So let's do that. Let me do that over here. If my r is 2, 2 is 1/3 of the height. So I am now going to multiply 3 to cancel that fraction. So my height is equal to 6. Now I can plug in 6 into my equation here. So this would be 6 squared and then the dH dt, which is 1.2. Now let's multiply everything out, and basically I have no more variables and I have it already solved for what I'm looking for. So dv dt is going to equal to 1/9 pi times 36 times 1.2. Now 36 times 1/9, that's 36 divided by 9, so this is 4. So I have now 4 pi times 1.2. And 4 times 1.2 is 4.8 pi. And now we have to have our units. So dv dt is equal to 4.8 pi. My units are inches, and this is volume, so this is going to be inches cubed per second. Let's try another cone problem to make sure that we understand. An inverted cone is 20 centimeters tall. So an inverted cone is exactly what I've been drawing. It's upside down. It is 20 centimeters tall. Has an opening radius of 8 centimeters. And was initially full of water. The water now drains from the cone at the constant rate of 15 cubic centimeters each second. So this here, this is dV dt. And I know it is dV dt again because of those units. It is cubic. The water is draining, so that means the volume is going to decrease. So this is negative 15 cubic centimeters per second. The water's surface level falls as a result. At what rate is the water level falling? So I am looking for dH dt. If they say water level, that's the height of the water. Or depth, that's also the height of the water. Okay, so at what rate is the water level falling? When the water is halfway down the cone. If the cone is 20 centimeters, what they just told us is that the height is 10 centimeters. So now, what are we going to do? We have here the h and dH dt and dV dt. We have my volume equation. We want this equation to only have h's. So the first thing I do with all of my cone problems is I create the ratio. R over h is 8 over 20, which can be simplified by 4, which is 2 over 5. Now, how do I know which variable I want to solve for? If I have dH dt, or I'm looking for dH dt, you look at the whatever rate you have or are looking for. If it's h, you're going to solve for r. If it's r, you're going to solve for h. Since I want dH dt, I am going to solve for r, meaning I'm going to multiply h to both sides. So my radius is 2/5 of the height. Now I'm going to take this ratio and I'm going to plug it in to my volume equation. So volume is going to equal to 1/3 pi, my radius, which is 2 over 5h squared times h. Now we apply the exponent, so this is 1/3 pi. 2 over 5 squared is 4 over 25 h squared times h. And now we multiply all of this out, so this is going to be 4 over 75 pi h to the third. This is my volume. At this point, once you have rewritten your volume equation, now we take the derivative. So dV dt is going to equal to 3 times 4 over 75 is 12 over 75. And 12 over 75 can be simplified by 3, which is 4 over 25. So 4 over 25 pi h squared dH dt. Once you've found your derivative, we're going to plug in everything that we have. So dV dt is negative 15 equals 4 over 25 pi. Now, I was given the h. I don't need to worry about this ratio anymore. See, unlike in this previous question, we were not given the h, we were given the r. So if that was the case, if we were given the r, we would use the ratio. That's why I box it, to remind myself that that exists, and plug it in to get the h. But I have it, so I'm going to plug it in, which is 10 squared, and I'm looking for dH dt. Now we're going to work on solving this. We got negative 15 is equal to 4 over 25 pi times 100 dH dt. This 100 and this 25 can be simplified. because 100 divided by 25 is 4. So negative 15 is going to equal to 4 pi times 4, which is 16 pi dh dt. And finally, I'm going to divide the 16 pi. So dh dt is going to equal to negative 15 over 16 pi, and my units are centimeters. Again, no exponent because this is height, not volume or area, so centimeters per second. So the volume here, the height is decreasing, which makes sense because now water is being drained from the cone. Moving along, let's try an extended problem. So we're going to look at a ladder situation. We got here a ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So let's look at what this means. Here we have the house. This is the wall of my house. We have a ladder that's leaning on the wall of the house, and the ladder is 25. What we end up here, this is the wall and this is the ladder, this is the ground. So we got a right triangle. Whenever you have a triangle, the equations that you're going to use to relate everything is usually the Pythagorean theorem. But we'll get there in a second. Now, I'm going to label the sides of my triangle so that I can use variables. This here, my ground, I'm going to call this x. And this, which is the height that the ladder is leaning on the wall, I'm going to call y. So let's see what else we're given. The base of the ladder is pulled away from the wall. This is the base of the ladder. It's being pulled this way. So what that means is that we're given dx dt because that's the rate at which this side of the triangle is changing. Now it's being pulled away, so if it's being pulled away, the distance between the ladder and the wall is going to increase. So that means that this rate is going to be a positive 2 feet per second. Now it says here, how fast is the top of the ladder moving down the wall? This is the top of the ladder, it's moving down. So we're looking for dy dt when the base of the ladder is 7 feet from the wall. So that means that x is equal to 7. So now remember what I said. This is a right triangle. That means that I'm going to use the Pythagorean theorem to relate all of these sides together. So we're going to use x squared plus y squared is equal to, now remember it's the legs squared added is equal to the hypotenuse squared. My x and the y here are always changing because the ladder is moving sideways and down. However, the length of this hypotenuse here, which is the length of the ladder is not going to increase or decrease. The ladder is a constant. It is 25 feet and it's not going to change. So I can plug in the number 25 squared. So this is the equation I'm going to use. Now let's see what happens when I take that derivative. This is going to be 2x dx dt plus 2y dy dt is equal to, now 25 squared is just a number, so this is going to equal to 0. Now look at all of the information we're given and what we need to plug in. I am looking for dy dt. I was given dx dt, and I have what x is equal to as well at that particular moment in time. The problem here is that I need y. In order to figure out y, and again, this is why I box things, is I can actually use this equation to figure out what the y is equal to at the moment that x is 7. So I'm going to plug in 7 for x, so 7 squared plus y squared is going to equal to 25 squared, which is 625. 7 squared is 49. So if I subtract 49, I get that y squared is equal to 576. And then when we square root, we get that at that moment in time, now let me go ahead here and use my calculator. The square root of 576 is 24. So now I have everything that I need. I can go ahead and plug in all of my variables. So 2 times x, which is 7, times dx dt, which is 2, plus 2 times y, which is 24, times dy dt is going to equal to 0. 2 times 7 is 14, times 2 is 28, plus 48 dy dt is equal to 0. Subtract the 28 to both sides. We get 48 dy dt is equal to negative 28, and then divide the 48. And if we simplify this, we can simplify it by 4. This is negative 7 over 12. And my units here would be the feet per second. Now again, use this to make sure that it makes sense with the question. Dy dt we just got is negative, and it should be negative because the ladder is going to be going down the wall, so that distance between the ladder and the ground is going to decrease. Let's look at part B. Consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So we're still talking about the same triangle here. The area of any triangle is 1/2 base, which the base is x, times the height, which is y. If we take the derivative, because we're trying to look for here dA dt. So if we take the derivative, we get dA dt is going to equal to, I have to use the product rule. So this is going to be my first function, this is the second. So the derivative of 1/2 x is 1/2 dx dt times y, plus, now I leave the 1/2 x alone, times the y, which is the derivative of y, which is dy dt. I have all of this information from this previous part because it's at the same exact moment when the ladder is 7 feet from the wall. So we're going to plug in all of these values. So dA dt is going to equal to 1/2 times the dx dt, which is 2, times the y that we got, which is 24, plus 1/2 times the x that we have here, which is the 7, times dy dt, which is negative 7 over 12. Now we just work this out. Half of 2 will cancel out, so we got 24 minus, because this is plus times a negative, 1/2 of 7, 7 over 2, times negative 7 over 12 would be 49 over 24. Now we can work with this, right? We can put this over the same denominator. So 24 I'd have to put over 24 and then multiply by 24. And 24 times 24 is 576 over 24 minus 49 over 24. So let's just see what that is. 576 minus 49, and we get 527 over 24. Now you can leave it like this, you can simplify it if you'd like, you can divide it. Honestly, it's fine. Like if I take 527 and divide it by 24, we get here 21.9583. And my units here, because this is area, this is going to be feet squared per second. Last one here, it says, find the rate at which the angle formed by the ladder and the wall of the house is changing. So we're looking for d theta dt when the base of the ladder is 7 feet from the wall. So at the exact same moment. So I can use my same exact triangle. Now just so you understand what angle they're talking about, if this is my triangle, it says the rate at which the angle formed by the ladder, this is my ladder, and the wall, so that means that this is theta, because that's what the angle that's between the ladder and the wall. Now, you can use any of the trigonometric functions. You can use sine, you can use cosine, you can use tangent. I will say that sine and cosine are the easier angles to use. So that would be up to you. I'm going to label the sides of my triangle here. This, if that's my angle, that means that this is my opposite side because it's directly across from the angle. This is always the hypotenuse, the diagonal. So that means that this is going to be the adjacent. I have that this is the x is equal to 7. I have that y is equal to, at that moment, 24. And the hypotenuse, which is always going to be 25. I'm going to go ahead, just to change things up from what we did earlier, I'm going to use sine. So sine of theta is going to equal to, remember that you can only plug in constants. Sine is the opposite over the hypotenuse. My opposite side, which is the x, that's always changing, so I can't plug in 7. I'm going to use x over the hypotenuse. The hypotenuse is never going to change, so that we're going to put 25. Now we're going to find the derivative. The derivative of sine is cosine theta, and then d theta dt is going to equal to, remember that this is 1 over 25 times x, so it'll be 1 over 25 dx dt. Now the cosine of theta, I don't need to know what theta is in order to know what the cosine is. Cosine is the adjacent over the hypotenuse. The adjacent side is 24, and the hypotenuse is 25. d theta dt is going to equal to 1 over 25 times dx dt, which once more is 2. So now to solve for d theta dt, I need to get rid of this fraction, so I'm going to multiply by the reciprocal. So d theta dt, look at this 25 down here and this 25 up here. This is going to cancel. So I get 2 over 24, and 2 over 24 can be simplified to 1 over 12. Now our units. Our units for d theta dt is always the same. It's always going to be radians, because that's always the unit that we use for angles. And it's going to be over whatever unit of time was given, which here is seconds. Let's look at another problem. I told you we would be practicing lots of different types. These are unrelated, so we're doing independent problems now. An airplane is flying at an altitude of 5 miles. So let me draw this out. So we got our little airplane here. Whatever. At an altitude of 5. Altitude is just a fancy word for height. So this is 5. And passes directly over a radar antenna. When the plane is 10 miles, so here's my antenna here. I'm just call this whatever, A for antenna. When the plane is 10 miles past the antenna, so let's say that it's over here. It's flying, so this is there. The rate at which the distance between the antenna and the plane is changing is 240 miles per hour. What is the speed of the plane? So if my plane was here and now my plane is here, this also forms now a right triangle. The altitude is not going to change because the plane is flying straight across. So this 5 is a constant. However, the plane is moving this way, so I'm going to call this x. And then let's say if the plane is over here, this is the distance between the plane and the antenna. So I'll call this y. Now what were we given here? We're given that when the plane is 10 miles past the antenna, so that is x. X is equal to 10. The rate at which the distance between the antenna and the plane is changing is 240 miles per hour. So what that means is that we're given dy dt, because if this is the distance between the plane and the antenna. So dy dt, now that distance is going to always increase because as the plane keeps going, it's going to get farther and farther away. So this is a positive 240 miles per hour. What is the speed of the plane? The speed of the plane is the rate at which the airplane is changing. So what we're looking for here is dx dt. Because this creates a right triangle, we're going to use the Pythagorean theorem once again. But now here, we're not given the hypotenuse, we're given one of the side lengths. So this is the only constant. X and y are always changing. So my equation is going to be x squared plus 5 squared is equal to y squared. Now I can take the derivative, which is 2x dx dt plus 0, because this is 0, is equal to 2y dy dt. Now I have the x, I have the dy dt, and I'm looking for dx dt. Once again, I'm missing the y. So in order to find the y, I'm going to use here my equation for the Pythagorean theorem. They're giving us that x is 10, so 10 squared plus 5 squared is going to equal to the y squared. 10 squared is 100 plus 5 squared is 25 is equal to y squared. So this is 125 is equal to y squared. If you square root both sides, we're going to get that y is equal to the square root of 125. Which, just to make this the rest of the question a little bit easier, we're going to go ahead and put that in the calculator and get the decimal. So the square root of 125 is 11.1803. So this is y. Now let's plug everything in. So 2 times x, which is 10, times dx dt, which is what I'm looking for, is going to equal to 2 times y, which is 11.1803, times dy dt, which is 240. This is 20 dx dt is going to equal to, now let's multiply this out, Oops, that's not what I meant. We have 2 times 11.1803 times 240, and we get 5,366.544. And then to solve for dx dt, we're going to divide that by 20. So dx dt is going to be the 5,366.544 divided by 20, which is 268.3272. And our units is going to be in miles per hour. For this next one, we have the radius of a sphere is increasing at a rate of 2 inches per minute. So I got here dr dt. We're told it's increasing, so that's a positive 2 inches per minute. Find the rate of change of the surface area of the sphere. So we're looking for dA dt when the radius is 6 inches. Okay, so we have this information. If I'm looking for dA dt, that means that I need the surface area of a sphere, and that equation is 4 pi r squared. I'm going to go ahead and take that derivative. So dA dt is going to equal to 8 pi r dr dt. I have the radius, I have the dr dt, I can plug this in. So dA dt is equal to 8 pi times the radius, which is 6, times dr dt, which is 2. 8 pi times 6 is 48 pi, times 2 is 96 pi. So that was it for this one. And our units here would be inches squared per minute. We're reaching the end. Last question. A spherical balloon is expanding at a rate of 60 pi cubic inches per second. So cubic inches. This is dV dt. And it says expanding. Expanding meaning it's going to get bigger. So that is increasing. So this is a positive 60 pi cubic inches per second. How fast is the surface area of the balloon? So I'm looking for dA dt expanding when the radius of the balloon is 4 inches. Now the thing with this question, or the thing with any of these related rates question, there is never going to be anything in the question that you're not going to use. You're always going to use everything that's given in the question. So if we are given dV dt, that means that we're probably going to use it for something, but I'm looking for dA dt. So let's start here with what we're looking for and then see why we were given this dV dt. The surface area of a sphere, just like we did in the previous question, is A equals 4 pi r squared. So I want to see what the dA dt is. That's what I'm solving for. So dA dt is going to equal to 8 pi r dr dt. Here, what I notice is that I have the radius, but I don't have dr dt. That's exactly why we were given dV dt. I probably am going to use this to figure out what is dr dt. So in order to use this, that means I must need to use the volume of a sphere. So this is the equation for the volume of a sphere. let's get dv dt and see what happens. dv dt is equal to, when I find the derivative, would be 4 pi r squared dr dt. If I am given that dv dt is 60 pi, I can replace this with 60 pi. I am also given the radius, which is the 4. And look at that. I have dr dt that I can isolate and then later put it in here to solve for it. So let's go ahead and work this out. This is 60 pi is equal to 4 pi times 4 squared, which is 16. So 16 times 4 pi is 64 pi dr dt. Divide the 64 pi, and I get that dr dt. Now I can simplify this by 4. 60 divided by 4 is 15, and 64 divided by 4 is 16, and the pi's would cancel. So dr dt is 15 over 16 inches per second. I have now my dr dt, so I'm going to take this and I'm going to plug it in here for my dA dt. So dA dt is going to equal to 8 pi times the radius, which is 4, times 15 over 16. Multiply this out. 8 pi times 4 is 32 pi times 15 over 16. I can simplify this. 32 divided by 16 is 2. So this is 2 pi times 15, which is going to give me my dA dt of 30 pi, and then my units, inches squared per second. So now that we've done quite a bit of examples of related rates questions, you notice that a lot of them are very different. And it's almost impossible to get through all different kinds of related rates questions. So the best way of getting really good at this is just to keep practicing, which we'll be doing a lot in class. So I hope you found this helpful, and that's related rates.